All right, welcome to section 6.2, where we learn about the trigonometric form of a complex number. So to begin with, we are going to do a little bit of graphing and introduce you to the complex plane that you may or may not be familiar with. The idea with a complex number is it's said that the motivation, possibly for a complex number, comes from this equation, x squared plus 1 equals 0. You can think of this way. So if you went back historically a number of years ago, before Descartes' time, for instance, people would have thought, well, there's no answer to this problem. If I square any number, I'm going to either get 0 or a positive number. So this equation, you would say, has no solution. Okay, no real number exists for that. So the idea is we imagine that such a solution exists. So if we defined these two things, I to be the square root of negative 1, or we call that the imaginary unit, and then we defined I squared to be negative 1, well, what happened in this equation is we would generate a solution by opening up this new system of numbers that's based on these two quantities right here. So the idea would be if you replaced this with I, then of course I squared is really negative 1, and then negative 1 plus 1 is equal to 0. So that was kind of possibly a motivation behind that, and as we developed the complex numbers and looked at their properties, we began to see that they showed up in lots of different places. They certainly are zeros of polynomial functions. If you took college algebra, you may have learned that quantity, that idea. Okay, so a complex number, usually we represent by z. It has a real part, we usually call a, and it has an imaginary part that we usually call the bi part. Real numbers are a subset of complex numbers, so any real number is also a complex number. So this is the big set, and you have all these subsets of real numbers and so forth. So what we're going to do is start by graphing a complex number. And what we do, if you're not familiar with this, is you're used to the regular real xy plane. So now we've got a real and imaginary axis. So the real part is measured left-right. The imaginary part is measured up and down. So in this particular problem, the real part would be 5 and the imaginary part would be 4i. So it's really analogous to doing this. This is like an x value, so you'd be going to the right. This is analogous to a y value, so you would be going up. So when you plot this point, all you do is just go over 5 on the real axis, and then you go up, and then you put your dot right there. So that would be where that point is located. And we usually represent complex numbers with z, so that's where 5 plus 4i is located then. Okay, so I'm going to go through several of these and just show you the different things that can exist on this. Okay, on this one we have the complex number z equals 4i. Okay, there is not a real part there, so it has to be a 0. So the real part is 0. The imaginary part is going to be 4i. So like I said, this is like an x value. This is kind of like a y value. You can think of it that way. So this one, you would not move to the left and right. On the real, you would just go up 4, and you would be right on the imaginary axis. So that's where 4i is located on the complex plane. So we call this whole thing the complex plane. Okay, next problem, the real part is that part. The imaginary part is that part, so that's negative I. And again, what we would do, you can kind of think of this like plotting the point negative 1, negative 1. You would go to the left. I'm going to zoom on this just a little bit. We would go to the left when we do this, 1, and then we go down 1. So that's where that point would be located then, is right there. Okay, so you got negative 1 minus I. And then the next problem, if we have 5, that's the real part. The imaginary part would be understood to be 0i. Okay, so on this one, this is a real number, so we just go over on the real axis, and that's where 5 is located. So you're used to doing number lines. You know, when you graph linear inequalities, like if you had x greater than 5, you're used to putting a parenthesis and graphing to the right of that. Well, that axis is a part of the complex plane. So you can think of real numbers as being a part of the number line, representing what you're used to as the x-axis. Okay, so let's go ahead and I'll let you guys work on a few of these. I'm going to let you work on number 6, and then on the next page, number 7 and 8. We'll just do these real quick. You got to make sure that you know how to do this before you can really understand the concept between trigonometric form of complex numbers. So with this problem, the real part is -3. The imaginary part is I. So you would go to the left 3 on the real axis, up 1, and put your dot there. So that's where that's located. Okay, on the next page, we have -6. So the real part's -6. This is understood to be -6 plus 0i. So that's your imaginary part. So this one would be just on the real axis, right there. Right, and then problem number 8, you got 6i. That's, of course, is the imaginary part. Real part 0, because you can think of this problem as 0 plus 6i. So that just means go up 6 on the imaginary axis. So that's where that number is located. Okay, and then the last one here is real part -2, imaginary part -3i. Okay, that means go to the left 2 on the real axis and then down 3 on the imaginary axis. So that's where that complex number is located on the complex plane. All right, so that's a very simple thing to do. Next thing we're going to do is look at the idea of a complex number. This is my little joke I found on the internet. It says, I can barely see that, it says, am I real? Okay, or something like that. Okay, it looks like the psychiatrist is on there examining the imaginary unit. Ha ha. All right, so let's look at what we mean by the absolute value of a complex number, and we'll kind of begin to look at that a little bit. So the idea basically is this. I'm going to just do a graph over here real quick, and I'm going to represent this just on a complex plane. So I'm going to have you draw out a coordinate system here. Let's just kind of look at this part of this where we would have, this is like the real axis and this is like the imaginary axis, like that. So the way we define this is a complex number. Let's just say we have a complex number a plus bi somewhere on the complex plane. Doesn't really matter where. And if we were going to go through and take the origin, 0, 0, and we just drew a radius to that, okay, we'd call that the radius. And then what you could do is you can make a triangle out of this like we've done in trigonometry since our beginning of our study. So this base of this triangle would be A. That would be the real component of the complex number. This height of this triangle would be B. That would be the imaginary part, like this. And then you have some sort of an angle theta. Well, we already know from the Pythagorean theorem that the square of the hypotenuse is equal to the sum of the squares of the two legs. So you get this. If you square root both sides, then you're going to get, of course, r equals the square root of a squared plus b squared. Well, it turns out that this quantity r is the same thing as the absolute value of that complex number, and we call that a modulus. Okay, so all really an absolute value of a complex number is it's really the distance from the origin to wherever that point on the complex plane is. So you can think of that in this situation as just the hypotenuse of a right triangle as the distance that you're locating. And of course, distance is always a positive quantity too. Okay, so this is what I just showed you is the radius r can be thought of as the modulus. It comes from the Pythagorean theorem. So we're going to crunch out on here the modulus of some different complex numbers. It's a real simple thing to do. So to begin with this example, when we do this, if you plotted this point, this is the real part, and then of course that's the imaginary part. So you would be going over 4 and up a smidgen. Smidgen's not a very precise mathematical term. So up 3/8 like that. So you'd be in there. And of course, what this is representing is you're really looking at the hypotenuse, or just think of it as a radius of a circle. You know, if you look at it like that, there's your radius like that. You're trying to find that distance, and of course what you have on this is you have a circle going around that like this. You don't have to do all this, graph all this stuff out. I'm just more or less trying to make a point that this modulus can be thought of as a radius of a circle with a center of 0, 0. Okay, and the complex number is on that circle. Okay, so when we do this, we're just going to crunch out r is equal to the square root of a squared plus b squared. So in your complex number, 4 plus 3/8 I, that's a, that's b. So it's really an arithmetic problem. So let's crunch it out. So a is going to be 4, b is going to be 3/8, and we're going to square that. Okay, so then we're going to have 16. This is going to be 9 over 64. You can get a common denominator, so I'm going to write that as 16 over 1 plus 9 over 64. So I need to multiply this by 64 over 64 to introduce that common denominator. Okay, then what I'm going to have is, if you multiply this out, I think that's 1,024 over 64 plus 9 over 64. Okay, and then this is going to be equal to 1,033 over 64 when we add the fractions. And you can break this up into the square root of the numerator and square root of the denominator. We have that square root property. So you would end up getting the quantity 1,033 square root of over 8. So what we're saying on this is r is equal to the square root of 1,033 over 8, and what that represents is the absolute value of that complex number. Okay, so that would be the idea of what the modulus or that absolute value is. Okay, now that one you got to do some fraction arithmetic on, which you have to do. So that one's just a direct application of the Pythagorean theorem. Okay, now if I go to the next page here, what you want to do is start by graphing this complex number. So this is the real part, negative 7 plus 0i. So what this one would mean is you would go to the left 7 on the real axis, and that's where that's located. So that's negative 7 on the complex plane. Well, you could go through and work out the Pythagorean theorem. You could do this formula if you want to, and it's fine. You would get a fine answer. Of course, a is negative 7, b is 0, so you got negative 7 squared plus 0 squared. So that's going to be equal to the square root of 49 plus 0, or that's going to be square root of 49, so that's going to be equal to 7. Okay, so what we just found is this, and you already know this. The absolute value of negative 7 is 7. Okay, now again, this means this. The mathematical meaning of this is it's the distance from the origin to that point, and what that is meaning mathematically speaking is you have a circle like this, and what you've got going on this problem is you're looking at the radius of that circle, and in this particular problem you can really just count that out. Okay, so you don't have to use that formula. So that's the idea. Okay, so that's kind of cool. You already know that. Okay, and that, so you can think of real numbers as just a part of the complex plane, just like the x-axis kind of. Okay, so it works out. Okay, so what I would like you all to do is go ahead and try the next two problems. Give you a little time to do those two problems. Make sure you've got the modulus. Do a graph. I think it's important to always do graphs on these problems because if you do a graph, it helps you understand the concept and it reinforces it. All right, so here's what you should have come up with on this. Of course, we got 5 plus 5i, okay, and we're going to try to find the absolute value of that. Now, you can go directly to the formula if you want to. That's a, that's b. And the formula, again, says to take a squared plus b squared like that. And you can go directly that way. I always like to try to get students to plot this stuff out to reinforce the concept. So if you plot this out, you should have went to the right 5 and up 5 on the complex plane to do that. And see what this is that's a radius of a circle again. You're finding r. So all you're really doing is you have a right triangle with the base of 5 and a height of 5 like that. All right, so you just go to the Pythagorean theorem. So you would end up having square root of 25 plus 25. So that is the square root of 50. So that we can break that down into the square root of 25 times 2. So that is 5 radical 2. So that means the modulus is 5 radical 2. Again, that means the absolute value of 5 plus 5i. It's that distance, okay? And again, you got that circle going around that then. Okay, next problem. Okay, this represents the number 0 minus 2i, okay? And you could immediately go through, when you do the absolute value of 0 minus 2i, again, you can go directly to the formula, which says take a squared plus b squared, and then take the square root of the sum of those squares. So we can go 0 squared plus negative 2 squared. Don't put the I in there. Then we would have 0 plus 4. So that's the square root of 4. So that's equal to 2. So you would have the modulus is 2. What that means, again, is that's what the absolute value of negative 2i is. Okay? So again, when you plot this point, what you would have done is you would have went just straight down on the axis like that. And again, you're finding the radius of a circle that has that particular radius of 2, like this. Okay, so it's kind of tedious to draw that circle on there, but you get the point. So all you're looking for is this radius. And see, on this problem, you can just count it. If your complex number is on an axis, you don't really have to use this formula. You can just count it and tell what you have. Okay? Right, so that'll take care of the modulus, which is a pretty easy concept to do. Just if you remember, it's a radius of a circle. It's the distance from the complex number to the origin. Then it's a real easy thing to develop. All right, now we're going to look at the trigonometric form of a complex number. So it turns out that any complex number can be written in terms of the sine and cosine function, which is kind of a weird idea. But what it ends up doing is it ends up, in many cases, simplifying calculations we do with complex numbers. So let's do this. Go ahead and just put a point somewhere, on your complex plane. And again, we're going to label that a plus bi, like that. Okay, now what we know is we're going to go ahead and draw a radius to that. So go from the center to that complex number like that. And what we're going to do is we're going to make a triangle out of this like we've been doing a lot. So just go straight down to the real axis at a right angle to form a right triangle. That's going to give us an angle theta. This side of the triangle is going to be represented by A. This part is going to be the imaginary part represented by B. So we're going to look at some real simple connections that exist on this. So if we did the cosine of theta is the adjacent over the hypotenuse. So the hypotenuse is represented by R. So the cosine would be A over R. Okay, now we can take that expression that we already know, so that's A over R, and we can solve that for R. So I'm going to multiply both sides by R. That will divide that out, and you're going to end up with the quantity A is equal to R cosine theta. Okay, so that's what this whole side of this triangle is represented by, it's represented by that quantity. Okay, so that means A, we're going to write that as R cosine theta. Okay, now we're going to go on and we're going to do this. Let's figure out what the sine of theta is. The sine, by definition of an angle in a right triangle, is side opposite over hypotenuse, so that's going to give B over R. Again, by the same thought process, we can multiply both sides by R to divide out the R and solve the equation for B, so I get B is equal to R sine theta. Okay, so what that means is this side of the triangle is represented by R sine theta. All right, so we're going to write that conclusion down as b is equal to r sine theta. All right, now we're going to put this together now. So what is r? Well, we said that r was the absolute value of the complex number, or what we call the modulus. Okay, so that's what that was. Now what we're going to do is we're going to use this information to build the trigonometric form of a complex number. Okay, so what we're going to do is we're working with a plus bi, and we're going to do some very simple substitutions. We're going to substitute r cosine theta in there, and we're going to substitute r sine theta in there. So you just want to go ahead and do that. All right, let's do that and write it down. So A, you're going to put in r cosine theta, plus B, let's put in r sine theta, and let's put times I like that. Now we're going to factor out the r. You have a common factor of r, so you want to remove that common factor. So that's going to be written as r times cosine theta plus I times sine theta. And then that would be what we call the trigonometric form of a complex number. Okay? So that's what our conclusion, that's what I showed you how to develop, is this thing right here. That's called the trigonometric form of a complex number. Okay? So we generally say z is equal to r times cosine theta plus I sine theta. One way you can remember this is r cis theta. Okay? That's just sort of a mnemonic device, really, is all it is. R is the radius, that's the modulus of the complex number. C is the cosine. I is the imaginary number unit. S is the sine theta. So if you think of r cis theta, be sure you spell it right, then that'll be a nifty way to remember the trigonometric form of a complex number. We oftentimes call this the polar form too. I think our textbook tends to use the trigonometric form. All right. So we're going to do some conversions on this, and to start with, I always recommend that you graph your complex number, okay? Instead of just going to formulas, don't use your calculator unless you have to, okay? You want to keep re-emphasizing the unit circle and the meaning. So to begin with on this problem, what I'm going to have you do is let's draw a complex plane. And let's do that on both of these problems. Just kind of get a complex plane put together. And these will be examples of problems that you can do very easily in your head. And just taking the time to draw this out will help you to understand this. So you're really doing the complex number negative 4 plus 0i. Okay, you got your real axis and the imaginary axis. This just means, of course, to go to the left 4 on the real axis. Okay, now all you have to do is you got to do two things. First thing you got to do is you got to figure out what is the radius. The radius of the circle that goes around this complex number is just going to be 4. You do not have to use the formula for the modulus or the Pythagorean theorem to do that. That's 4. Okay, the radius of a circle is always positive. Now you got to figure out the angle, but the angle, you don't have to use a calculator or unit circle. There it is. It's 180 degrees. So typically, we could use pi. If I wanted the answer in radians, you could use pi. Typically, most of the time, we use degrees on this. So we're going to be now ready to write this out. You could also use negative 180 if you wanted to. There's actually many ways you could write that angle. The standard way to do this oftentimes is just to use a positive angle or that's between 0 and 360. You can also use a negative angle that's between 0 and negative 360 if you want to. So it goes like this. Okay, we've got r cis theta. That's a real easy way to remember your complex number. So the radius is 4. Then you put a parenthesis. C stands for the cosine. So we say the cosine of 180 degrees plus the I part. That comes next. And then S, of course, stands for sine 180 degrees. So that would be what we call the trigonometric form of that complex number. So believe it or not, you didn't learn this in middle school, You learned about negative numbers, but no one taught you that negative 4 is really the same thing as 4 cosine 180 plus I sine 180. And believe me, it is. So you can represent any real number as a form, a trigonometric form with sines and cosines in it. Okay, because every number can be represented by a radius of a circle. That's what it boils down to. Okay, now the next problem. This one, of course, is really 0 minus 3i. So that just means you're going to go down 3 on the imaginary axis. You can kind of visualize having a circle going around that if you want to. Right? Your job, excuse me, is to do two things. You want to figure out the radius. The radius is just that quantity right there, which is just 3. Okay, then the angle, you got two choices. You could do 270 degrees if you'd like. You could also go clockwise, and you could use negative 90 degrees as you like. Okay, so you could write the answer in two ways. R cis theta, you say 3 cosine of 270 degrees plus I times the sine of 270 degrees, like that. Or you could say 3 cosine of negative 90 degrees plus I times the sine of negative 90 degrees. And those are two ways to write the answer to the problem. Doesn't matter which way, they're both the same. Okay? Okay. Now, moving on. I'm going to do one more. This one, you have to do a little bit more work on this problem. So with this one, the idea is going to be, first of all, find the radius. Now let's draw a picture. Pictures are always very helpful to help you understand these problems. So I'm going to put a complex plane at the side here. Now all that really matters on this problem, when I graph out negative 4 root 2 plus 4i root 2, is you're going left on the real axis and you're going up on the imaginary axis. So just do this. Just go left a little bit and then go up like that. And then we're going to go ahead and we're going to draw our radius on that, and we're going to draw our circle so we can visualize what's going on in the problem. Okay, so that's what we're going to have for our radius. So let's go ahead and label that as R. And then we can go ahead and make our right triangle. Okay, and these sides are going to be represented by, the base of the triangle is 4 radical 2. That's the base. You can think of that value as negative since you're going to the left, so I'm just going to put it like that. Okay, that's the value of A from your complex number. And then this side of the triangle could be represented by 4 root 2. And then that's the value of B like that. So if we're going to do the radius, well, we can go ahead immediately and go to the Pythagorean theorem. We can't do this in our head, so we have to do this. So one thing we can do is R squared is equal to A squared plus B squared. So that's going to be R squared equals 4 times the square root of 2 squared plus negative 4 times the square root of 2 squared, like that. Now, I want to focus on this little slice right there, because I see students make mistakes on this all the time. And the thing that I see students do all the time on this, I'll see students go through, write it out twice, and then they'll try to do FOIL on it. They'll try to go, okay, first, outer, inner, last. Okay, guys, this is not a FOIL problem. FOIL looks like this. If you have 4 plus root 2, and 4 plus root 2, yes, you can go through and do the first, out, and all that stuff. Okay, that's not what that is. So you just multiply this. So you just go 4 times 4 is 16. Then you take the square root of 2 and square that, and the radical comes off, so you get 16 times 2, so you get 32. Okay, so you end up having this quantity right here is going to be 32. Again, that's 4 root 2 times 4 root 2. Is 16. You can think of it as 16 times the square root of 4 if you want to. Okay, so that would end up being 32 there, and then 32 there. Okay, so that's now going to give us, of course, that's 64. So we have R squared equals 64. Square root both sides, we're going to get the radius is equal to 8. So that's going to be a part of our trigonometric form of our complex number. Okay, now what you want to do, and you want to be careful about this, is we're going to ultimately find that value of theta. But we'd like to find this reference angle, and I'm going to call that like theta prime. I use that a lot of times for a reference angle. And what you can do on this is you can evaluate the tangent. So one thing you know is the tangent of that angle that I'm going to call theta prime is opposite over adjacent. So it's 4 root 2 over negative 4 root 2. All that stuff divides out, so you get the inverse, or the tangent of theta equals negative 1. Okay? Now, what I want to do with this, next thing here is we can think about the unit circle if we want to. So one thing that you'll notice on the unit circle, if you went through and just looked at this point, if you have a unit circle, you have this point in quadrant 2 that's negative root 2 over 2, root 2 over 2, okay, which has a 45-degree reference angle, or 135 degrees. Okay, well, that's what happens is the tangent of 135 degrees is just equal to y over x, which is equal to negative 1. Okay, so what you'd end up having is a 135-degree angle. Okay, like that. So you're just doing an inverse tangent on that. Now you want to look at the unit circle, and the thing is, you know, you'll get used to this. If you see a square root of 2, and these two numbers are the same, that's what told me that it was on the unit circle. Square root of 2s we know are on the unit circle, so that's what clued me to that fact. Okay, now what I'm going to do is put it all together. So the answer is r cis theta, okay? So that would be your answer to your problem. R cis, there's your I, like that, okay? So the problem's done. So that would be how that complex number goes. Okay, so let's work two problems out. Give you a little time to see if you can figure out how to do number 19 and 20. All right, so let's make sure we got everything put together correctly. Now again, hopefully you followed my recommendation of drawing a picture on these things. So what you're working out with this one is the complex number 0 plus 5i. You should have went up 5. Put your dot there. This one is very easy to do. You can do this one very quickly. Okay, the radius of that circle is the distance from there to there. So remember, you got a circle going around those points like that, so that radius is 5. And that angle, I would say use 90 degrees. If you use negative 270, it's also right. So let's just use that. So the final answer of the problem you should have got is 5 parentheses, cosine of 90 degrees, plus I times the sine of 90 degrees. And that would be your trigonometric form of your complex number. So if the complex number is on an axis, it's very easy to do. All right, with the next problem, let's again put a coordinate system on here so we can reason this one out pretty well visually. So I'm going to put a coordinate system over here. Let's see. So let's get that set together here. Okay, so what this one is you've got the complex number 2 root 3 minus 2i. So you're going to the right on the real axis and down on the imaginary. So for all practical purposes, all that matters is that we're down somewhere in this quadrant. We're in quadrant 4, we're to the right, and then we're down. Okay, so what we want to do with this one again is figure out what the radius of the circle is. So we want to go ahead and just draw a little picture of the radius like that. Then, of course, you've got a circle that's going around that point like that. And what we need to do is we need to find r, and we're going to need to find theta. So we're going to make a triangle out of that. And, of course, the A is this thing there, so we could represent that part of the triangle by this. And then B is this, and I'm going to put negative 2 there. Technically, that side of the triangle is negative 2. But I'm going to put negative 2 there. All right, so what we want to do is we want to start by crunching out the radius, and that requires the Pythagorean relationship. We're going to do r squared equals a squared plus b squared. So you should have done r squared equals 2 root 3 squared plus negative 2 squared. Okay, this part right here is going to be 2 squared is 4. That's the square root of 9, or the radical comes off. Either way you want to look at that. So this is going to be 4 times 3 or 12. 12 plus 4. So you're going to have r squared equals 16. Square root both sides. A radius of a circle is always positive. So we get 4. Okay, now our job is to find the angle. Now what we're going to do is we're going to find this reference angle that I'm going to call theta prime right there. And there's a couple things. Well, first of all, you see that you have a square root of 3, so you pretty well know you're probably on the unit circle. Okay, so there are several ways to do this. One way you could do this is the tangent of this theta prime is this value opposite over adjacent, or you can think of it as y over x if you want to, like you're familiar with. So we just do that. Okay, then you could do that. That would be tangent of theta prime equals negative 1 over root 3. Okay, well, that's one of the places on the unit circle, so let's figure out which place it is then. So what you would find on this is you will find on the unit circle a couple of points on there. One point that you would find on a unit circle, and I'm going to just put this up here. You have these 2 points kind of like this. This point right here is root 3 over 2 1/2 with a negative 1/2. And then this point is root 3 over 2. No, I'm doing that backwards. Okay, that's 1/2. And then negative square root of 3 over 2 like that. Okay, so the question is, which one is it? Well, if you look at doing this one, if you did y over x on this, what you would have is negative 1/2 over root 3 over 2, with the 2's crossing out. So that gives negative 1 over root 3. So you would be looking at that reference angle there of 30 degrees. So what you reason out on this then is this angle right here, that reference angle is 30 degrees. Okay, so what you can do is for theta, you could use 330, or you could even use negative 30. It doesn't make any difference. A lot of times you'll see textbooks use the smaller, the angle with the smaller absolute value. To me, it doesn't make any difference. So I'm just going to go ahead and use 330, but if you use negative 30, it doesn't matter. So the final answer would be r, and then we do the cosine of 330 plus I times the sine of 330. And that would be the answer to that problem, like that. Now, I do want to show you one other thing. I'm going to erase this diagram that I put over here, and I'm going to show you a way that I would look at this problem. I wouldn't go through that thought process on the angle. Let me show you what I would do. I just find it to be a little bit quicker. So if I did this, I would, again, go ahead and just draw, my reference triangle. So I've got, let's see, I've got the 2, I got the 2 root 3, and I've got an angle here, and then I can think of this as negative 2, like this. Well, one thing that you can do on this is if you divide that by 2 and divide that by 2, you're not changing that angle. You're changing the radius, but you're not changing that angle. So what you would end up having then is you could think of this as negative 1 now. You could think of this as square root of 3 now. So you got 1 square root of 3, 2. And then you can just think of the side opposite of that 1 would be 30 degrees. Okay, this is a 30-60 right triangle. Okay, with a radius of 2. But we're finding the angle, so it doesn't matter what the radius is. Okay, so that's the way I would personally look at that problem then. Okay. Okay, so the next thing that we're going to go ahead and look at here is the idea of just doing what we just got through doing in reverse. And this is a very simple thing to do, actually. All right, so when we do this, mostly this is just multiplying out and doing the unit circle, so it's a very simple thing to do. Okay, so with this one, all we need to do is do the cosine and sine of 30. So this is just unit circle. So you're looking at this point. The cosine's the x value, so you would have 8 times, that's your cosine, square root of 3 over 2, plus I, and then of course the sine is 1/2. So you're going to multiply all that out. Just do a distributive property. So you're going to have 8 over 1 times square root of 3 over 2. Then you're going to take 8 times the rest. So you're going to have I times 8 over 1 times 1/2. Then you can reduce the fraction. So you have 8 root 3 over 2 plus 8 over 2 times I. And then 8 over 2 is 4. So you would end up getting 4 times the square root of 3 plus 4i as your solution to your problem. Okay, so all you're doing is just multiplying that out. That's it. All right, the next thing that I want to go through and look at is a few more examples that illustrate this idea. So we're going to do the same thing with this. We need to figure out the cosine and sine of 270. So at 270, you're looking at this point. So that's going to be cosine of 270 is the x value, so that's 0. Sine of 270 is the y value, so that is -1. So we're going to have 3 times 0 minus I, and then you can multiply that out, distributive property. 3 times 0 is 0. 3 times -I is minus 3i. And you want to write it that way. If I say write in the a plus bi form, you want to include that 0 when you do that, okay? All right, go ahead and try the next one. Okay, so what you should have here is just going through the unit circle. If you were to count out this, of course, that's -90 and then 45 more. So where you're located on the unit circle is there. So it's a matter of just locating those values. So you should have done 4. Cosine of -135 is the x value. So we want to write that as -√2 over 2. Put the I. The sine is also the same. It's the y value. So you're just going to multiply that out. So you're going to have 4. I'm going to put that over 1. -√2. I can't draw a square root today. Negative square root of 2 over 2 plus I times 4 over 1 times -√2 over 2, like that. I'm going to write that just as -4√2 over 2 minus 4√2 over 2. You can reduce, cross if you want to. So that will give the answer 4 over 2 is going to give -2 root 2. Same thing there. Minus, and don't forget your I, so we got the I in there somewhere. And actually the best way to write this is 2i root 2. So I would recommend that you develop the habit, if you have a radical, put the I in front of the radical. It looks better that way. The reason I want you to do that is because a lot of times students will write 2 root 2i, and they'll write it like that, and it looks to me like I is under the radical. I is never going to be under a radical when you're doing this type of problem. Okay, so don't do it that way, all right? Okay, so the next thing we're going to do is we're going to develop a formula for the product of complex numbers that are in trigonometric form. Okay, so I've gone through and done, already typed out some of the steps on this proof. And what I'm doing on this is I want to mainly get down to this point and see how we use an identity that we learned earlier in the semester. So the idea is I have 2 complex numbers. This would be in the first one, and this be in the second one, like that. So we are going to multiply those complex numbers together. So here's your first one, and we're going to multiply by that. So what we can do is, by using an associative property, we can multiply just the R1 and R2. You just multiply the 2 radiuses together, and then you need to multiply these 2 things out, and that's just multiplying 2 binomials. So you're going to do a distributive property, or if you want to, you can think of that as FOIL. So you're going to do cosine times cosine is going to give this. And then the outside term, you're going to have cosine times sine, and you're also going to have the I. So that's the result of that term. Okay. Then your inside term, you would have sine, cosine. So that'll give that. You also have the I. And then the last term, what you have, and I made a mistake on that. You have I times I, so you need to write that as I to the second. Shame on me. Then I got sine, like that. So if you look through that, you should be able to follow that that is a distributive property or FOIL, if you want to call it that. And we're going to look at a couple of things on this. So I'm going to have you write down a few more steps. Let's bring this down, and that's R1, R2. And I'm going to put a big bracket here, and we're going to kind of group these things together now. I'm going to put the cosine theta 1, theta 2 there. Now see, this thing right here, I squared is -1, so this thing is going to become really negative sine theta 1, sine theta 2. So I'm going to go ahead and put that there. Okay, I'm grouping this together on purpose in a certain way, and I think you'll see this okay. I need to have a sign there, though. So I'm going to do sine theta 2. So what I did is I just put that together with that. All right, I'll need a little bit more room on this. Okay, now the next two, I'm just going to put them together. Okay, so, and they've both got i's in it, so I'm going to group together this thing and this thing. And there's both an I embedded in there, so we're going to just go ahead and write I, and then a parenthesis, cosine theta 1, sine theta 2, plus, and then this, sine theta 1, cosine theta 2, like that. So what I'm doing is I'm grouping this together in a certain way because there's going to be a couple of identities that pop up. Both of these had i's in them, see? So I went ahead and just factored that out like that. So I kind of skipped a step on there, but I think you can probably follow that okay. So then the next question is, do you recognize this? And do you recognize this? These are identities that we've learned how to do. All right, well, basically what this one is, this is the one that goes cosine, cosine, sine, sine, different sine. That is the cosine sum identity. So we're going to bring down the R1, R2, and we're going to replace this thing with cosine theta 1 plus theta 2. That's what that is. Cosine, cosine, sine, sine, different sine. Okay. And then this one goes cosine, sine, sine, cosine, same sign. You're more used to seeing this as this. Sine theta 1, cosine theta 2, plus cosine theta 1, sine theta 2. That's the way you're used to seeing this is sine, cosine, cosine, sine, same sign. And what that one is that's the sine of the sum of the two angles. Okay, so that's what you end up with is a formula for multiplying complex numbers, two complex numbers that are in the trigonometric form. So in general, what we conclude is if this is the first complex number, and that's the second complex number, this is the formula you would get when you multiply complex numbers. And it's very elegant. All you do is multiply the radius, whatever the radiuses are, multiply them. You add the two angles and do the cosine. That becomes your first part of that form. And then the I part, the imaginary part, you just add the angles and take the sine of it. Because it's a very elegant formula to me. It's a very beautiful formula, very simple. Okay, so let me show you how we're going to utilize this a little bit. So what we're going to do on this one is we've already got two numbers that are already written in the trigonometric form. So according to this formula, what we do is these two things. You multiply the radiuses. So you're going to do 5 times 2. Okay, then what you do is you add the angles and do the cosines. You're going to do cosine of 60 degrees plus 90 degrees plus I. You're still in that r cis theta form, see? Then you do sine, and then you add those angles together. Okay, so we got that. And then we would have 10 times the cosine of 150 degrees plus I times the sine of 150 degrees, like that. So now, if I wanted the answer in polar form, you're already done. Okay, the problem's done if I say write the answer in trigonometric form, but I want this in a plus bi form, so we're going to go ahead and we're just going to crunch this out then. So the cosine, just look up 150, so here's 150. That's the cosine's the x value, and we know the sine's the y value. So what you would end up having then is you would have cosine of 150 is this thing. So let's write negative square root of 3 over 2 plus I. The sine of 150 is this dude. Guys, you got that? So let's multiply it out. So we have 10 over 1 times negative root 3 over 2 plus 10 over 1 times 1/2 times I. Okay, just multiply it out. If you want to cancel out these, reduce these fractions, you can do it this way if you want to. So that's 5. Same thing there, that's 5. So the answer to the problem looks like it's going to be, this part right here is going to be negative square root of 3, or negative 5 times square root of 3. Don't forget about your 5. Okay, so we got negative 5 radical 3. And then this part of the problem, you've got 5i. So it's pretty simple, okay? If you're in polar form, it's very, very easy to just multiply out those two complex numbers. Very simple. Very elegant, as I said. Okay, so let's go ahead and pause for a minute here and do the next problem the same way I did that. Okay, so what you should have done on this, very simple to do, is just multiply the radiuses and then add the angle. So you'll do the cosine of 135 degrees plus 225 degrees, and then plus I times the sine of 135 degrees plus 225 degrees. Okay, like that. So you'll get 24 times the cosine of that looks like 360 degrees plus I times the sine of 360 degrees. Okay, and see, if I was looking for the answer in trigonometric form, you would be done. So we do want to go ahead and get these two things worked out. So if we're at 360 degrees, we know that we're one lap around the unit circle. So the cosine's 1 and the sine's 0. So you'd end up with 24 times 1 plus I times 0. So that's 24 times 1, really. Okay, so that would be 24. So you could write the answer as 24 plus 0i. Okay, I did say write it in a plus bi form, so you do need to write the answer like that. Okay, so actually, the number 24 can also be written this way. Who would have thought? It's kind of a complicated way to write 24, but it's right. Okay. Okay, so next thing I'll do is develop a different formula. And this one I'm just going to give to you. I'm not going to go through and prove this one. The proof is actually very similar, and it's kind of a good thing to try. If you're interested in trying, you can do that. I did notice I do have one key mistake on here that I definitely need you to correct. This is a really big deal. I wasn't paying attention. You need to scratch this thing out right here, and you need to replace that with this. That should be R1 over R2. So that's real important that you get that corrected. And what happens is if you divide two complex numbers, you end up dividing the radiuses, and then you subtract the angles, which is kind of interesting. So that's the way that one works out. So these are actually very simple to do. If you were doing number 28, the result of this, you would end up doing this. Okay, you would just go through and divide those two things. Okay, then you would do this. You would do the cosine and just subtract the two different angles. So you're going to do the cosine of 7 pi over 4 minus 9 pi over 4 plus the imaginary part I. Then you're going to do the sine of 7 pi over 4 minus 9 pi over 4, and then crunch everything out. Okay, so let's just do that the side. We got 7 pi over 4 minus 9 pi over 4. That's going to be negative 2 pi over 4. Okay, so that's going to be negative pi over 2 is what you get as your result on that then. Okay, so let's write this out. And one of the things where students oftentimes mess up on these problems is right here with that radical. I see that more often than anything else. You can write that in one radical, and you can reduce that 3/6. So you can reduce 3/6 down to 1/2 if you want to. And then this is going to be cosine of negative pi over 2 plus I sine of negative pi over 2, like that then. All right, so what I'm going to do then is when I finish this up, let's kind of work with the square root of 3 over 6 over here. That's of course, the square root of 3 over 6 is really the square root of 1/2. And you can break that up into the square root of 1 over the square root of 2, which of course is 1 over root 2. Then you can rationalize that denominator like we've been doing throughout the semester. So that would give square root of 2 over 2. All right, so I'm going to write this then as square root of 2 over 2 times cosine negative pi over 2 plus I times the sine of negative pi over 2, like that. Okay, so that's how that goes. And now see, if I want the answer in trig form, that's the trig form answer to the problem. But we're going to go ahead, look at the unit circle, and of course we're just going to crunch this out. So negative pi over 2, if you look at my unit circle up here, of course, you know, that's negative 90 degrees is this way. So you're going to be looking at this point right here. So basically the cosine is that, and then the sine is that. Okay, then you can take that information and get the final answer of the problem. So you get root 2 over 2, cosine of negative pi over 2 is 0, plus I, sine of negative pi over 2 is negative 1. So you end up getting negative root 2 over 2 times 0 minus I. And then you can do a distributive property. So that's 0 minus, and let's write I, root 2 over 2 like that. Okay, and that's in the a plus bi form. So that would be the quotient of those two complex numbers is what you would have. Okay. All right, so just one other little thing, and go to the next page, and I'm going to have you do problem number 29. You can refer to this unit circle if you want to, and let's do that for a few minutes, wrap that up, and then we'll go through one more. Okay, so here's what you should have done on this problem. Okay, first of all, divide the radius. The one radius is 5, the other one's 4, and then subtract the angle. So you're going to do cosine of 200 degrees minus 50 degrees plus I times the sine of 200 degrees minus 50 degrees. All right, that will give you 5/4 times the cosine of 150 degrees plus I times the sine of 150 degrees, like that. Okay, so that is the trigonometric form of the answer. So now we just need to look at the unit circle. Go to 150 degrees. Those are the points on the unit circle. So that's going to give 5/4. Cosine of 150 is negative root 3 over 2. Sine of 150 is the y value, so that's 1/2 times I, and then multiply it out. Okay, there's no reducing on this problem, so if you multiply that out, you're going to get negative 5 root 3 over 8, it looks like. And if you multiply that out, you're going to get plus 5/8 I, like that. All right, so that should be the a plus bi form of that answer. All right, so the next thing we're going to look at is what we call complex conjugates, which would be something that you learned about in the past. So to begin with, let's draw a picture. So let's put a complex number here, and let's call that a plus bi. And let's draw the radius to that like we've been doing. So we need to identify that radius. That will be kind of important. And then let's make our triangle on this. Okay, so we're going to have this, and we're going to call that theta, and we're going to call that r to begin with. Okay, now, one thing you probably learned in college algebra or pre-calculus is a conjugate. A complex conjugate just means you change that sign. You don't change anything else. The plus becomes minus. So what that means is that complex conjugate is a minus bi, and if we graphed that, we would go over a and then we would go down, but that angle would be the same reference angle. Okay, it's just one little slight difference to it. So let's go ahead and let's graph that. So I'm going to, again, on this, let's just put a radius like we did before. Trying to make the angle the same. All right, so what we're going to have is this point is going to be the conjugate, a minus bi. And again, you can make a right triangle to that, and I'm going to call that theta and maybe theta prime, like that. Okay? Well, the thing is, if you do this, really all this is going to become is if this is theta, that's just going to be negative theta. So I'm going to replace that, have you replace that angle with negative theta, because you're going clockwise. So it's just as easy to write that angle like that. And that's all we need to develop a formula for a complex conjugate. Okay, so if we're doing this, and if we're writing this in the r cis theta form, then it goes like this. So what we'd end up having with this, if you have a minus bi, you could write this, if you wanted to, as a plus negative bi, like that. And then you could go through and put that in the r cis theta form. So it end up going like this. Okay, if you did this, you would just end up having the radius r, and then you would have the cosine of that angle, which would be now negative theta, and plus I times the sine of that angle, negative theta, like that. So it just means the same thing. You've got the radius r here, you have that angle there, so it's still going to be written like that. So really, it turns out on a complex conjugate, you just change the angle to opposite. Okay, doesn't matter where that angle is. That original complex number could be anywhere on the complex plane, and this would end up giving the complex conjugate then, right? So basically, here's the formula we got. Now I'm going to show you a couple of things here. Is try to make a couple of connections on this. If you multiplied these two complex numbers that are in the a plus bi form, let's go ahead and multiply these two things out, and let's see what we get. So if we do that, you could think of this as FOIL. So the first term, a times a, is a to the second. The outside term, a times negative b, is negative ab times I. That term, back to doing the distributive property, so that's going to be plus abi. And then this term, you have a positive times a negative, so that's negative b squared, I squared. Okay, those things divide out, or not divide out, they subtract and cancel, if you want to think of it that way. Then this is a squared minus b squared, and then we know this is negative 1. So we end up with a squared minus, and then that's going to be negative b squared times negative 1. Hold on, I'm not doing that right. I'm having a hard time looking out the window at the beautiful mountains and concentrating at the same time here. At least that's my excuse. Okay, so we've got a squared minus b squared times negative 1, and then that gives a squared plus b squared. Okay, so that's how you multiply, of course, complex numbers if they're in the a plus bi form. Now we're going to see what happens if we multiply them out in this form. Okay, and remember, we already developed a formula for this, so if you do this multiplication, what do? You multiply r times r, which really gives you r squared. Then remember what we do is we do the cosine of the sum of those angles. So we're going to do theta plus negative theta plus I times the sine of theta plus negative theta. I'm applying what we just learned previously as how to multiply complex numbers in the trigonometric form. So what this is going to give is r squared times the cosine of 0 plus I times the sine of 0. Not theta, 0. Okay, so we got that. And of course, we can do the unit circle. So on a unit circle, you got the point 1, 0. So that's going to give r squared. Cosine of 0 is 1. Sine of 0 is 0. So you end up getting r squared times 1 plus 0i. Or really, you just get r squared. because you're doing r squared times 1, you can think of that as r squared plus 0i. So we just write that as r squared. So that means the result is this. So that's real cool. I mean, if you multiply a complex number by its conjugate, you square the radius. So you get these real simple results on these problems. That just fascinates me. Come up with these elegant, beautiful, simple mathematical formulas. Okay. All right. So let's do one more thing on this then. And I just did the proof on that. So really, what I just showed you is you have r squared, cosine, add the angles, you get 0. Plus I sine, add the angles, you get 0. That gave r squared times 1 plus 0i, so that gave r squared. Okay, so all you got to do on this is you're going to do these problems real quickly. These are real simple problems to do. You're going to take this complex number, you're going to determine the complex conjugate in trigonometric form. So there's nothing to this. Okay, so usually what we say is we say z is equal to the given complex number. And then the complex conjugate, we often write that as z bar. So z bar, all you do is change the angles to opposites. So that's going to be cosine of negative pi over 4 plus I times the sine of negative pi over 4. The complex conjugate is very simple. You change the angle. What kind of fascinates me about that is when you learned about conjugates like this, like you learned 3 plus 4i, its conjugate is 3 minus 4i. You change the sign. Well, in polar form, you change the angle. That's kind of cool. All right, so this one goes like this. This is z, so z bar would be 6 radical 2. And then you just need to change these angles to opposites. So the opposite of 70 is, a negative 70 is 70 degrees. And that would be I sine 70 degrees like that. That's it. That's your conjugate. So that's all you got to do if it's in trigonometric form. Okay, so the last thing we're going to do, very simple, is this problem says find the product of the given complex number and its conjugate. So what we're doing is we're taking this complex number, written in trigonometric form, and we're going to multiply it by its conjugate. Well, its conjugate is just 6 times cosine negative pi over 4 plus I sine negative pi over 4, like that. Okay, so we're going to multiply those two things like that. And it turns out that all you do is you take this number and square it. Answer's 36, guarantee. That's all you do. If you forgot that, I mean, it would work out like this. If you forgot that all you do is square the radius on this, then you could do 6 times 6 times the cosine of pi over 4 plus negative pi over 4 plus I times the sine of pi over 4 plus negative pi over 4, like that. So that's 36 cosine of 0 plus I sine of 0. And then you would end up getting 36 times 1 plus 0i. So you get 36. So if you forget this simple formula, you can do that if you want to. Okay? All right, so the next problem, we're taking this number, and we're going to multiply it by the complex conjugate in trig form. So the conjugate's going to be 5 root 2 times cosine of negative 40 degrees plus I times the sine of negative 40 degrees, like that. So here is your given complex number. Here's your conjugate. Notice the only difference is these signs. All right, now all you got to do, you don't have to multiply the whole thing out. All you got to do is take this thing, the radius, and you square it, and then you have the answer to this problem. You can do that in your head if you want to. Okay, that's 5 squared, and it's the square root of 2 squared. So that's 25 times 2. So the answer to that problem is 50. Okay, so that's a very simple thing to do. And these formulas are actually pretty easy to derive if you forget those. Okay, so that will wrap up everything we need to know in this section. It's a very abstract section. It's not a hard section to learn. Most of the trigonometry relates very nicely to the unit circle. So I hope that helps you to learn the material in this section.